right, let's dive right in. Today, we're going to tackle one of the weirdest, most fundamental rules in all of physics, the principle of superposition. And we're going straight to the source, to one of the original pioneers, P.A.M. Dirac, to understand this idea that basically throws our common sense right out the window.
So right off the bat, Dirac is telling us, hey, everything you think you know about how the world works, you gotta let that go. The real rules of the universe, they don't operate on a level we can easily imagine. He's saying that to get to the truth, we have to wrestle with a much deeper, more abstract reality. This quote, it's basically the key we need to unlock the whole quantum world.
So, you might be asking, why did we need such a wild new way of thinking in the first place? Well, it's because by the turn of the 20th century, the beautiful, predictable machine of classical physics was, well, it was breaking. There were huge cracks showing up everywhere, problems that the old rules just couldn't explain.
And look, we're not talking about small little rounding errors here. These were massive fundamental failures. I mean, the old physics predicted that atoms should completely self-destruct in a fraction of a second, but they don't. It had no explanation for why atoms only give off light in very specific, discrete colors. And of course, the big one, what even is light? A wave? A particle? Classical physics had no answer. The old way of thinking was fundamentally broken.
Honestly, physics was in a full-blown crisis. This wasn't something you could just patch up with a new equation here or there. The very concepts they were using to describe reality were failing. They needed a revolution. And that revolution came from an idea that would completely rewrite the rulebook. And here it is, the hero of our story, the principle of superposition. It is the strange, counterintuitive, and unbelievably powerful idea that sits at the very heart of quantum mechanics.
Okay, so what is it? In our everyday world, a coin is either heads or tails. It can't be both. But in the quantum world, an electron can be in a state of spin up and spin down simultaneously. Now, this isn't just us not knowing which state it's in. No, quantum mechanics says the electron truly exists in this bizarre, combined, fuzzy state of potential, right up until you measure it.
And this is where it gets really, really different from anything we're used to. If you add two waves in a pond, you get another intermediate-sized wave. Makes sense. But if you measure a quantum system that's in a superposition of state A and state B, you don't get some wishy-washy state in the middle. No way. You get either 100% state A or 100% state B. The in-between nature of superposition only exists in the probabilities, the chances of which one you're going to get.
I know, this all sounds incredibly abstract. So let's use an example straight from Dirac's own work to see how this principle has very real, measurable effects. We're going to zoom in on the strange life of a single particle of light, a photon.
Okay, imagine a special crystal that acts like a fence with only vertical slots. It only lets vertically oriented light pass through. Now, what happens if you fire a single photon at it that's polarized at a 45-degree angle? Does half of it get through? Does it get stuck? Classical physics has no idea. But quantum mechanics has an answer. It says that 45-degree photon is in a superposition of being both vertical and horizontal at the same time. The moment it hits that crystal, it is forced to choose. It either passes through completely and becomes vertically polarized in the process, or it gets absorbed completely. It's an all-or-nothing game.
And this is where it stops being philosophy and becomes real science. This isn't just a fun story. It leads to a precise, testable prediction. Dirac showed that if the photon's polarization angle is alpha, the probability of it making it through the crystal is exactly sine squared alpha. This bizarre idea about a fuzzy reality leads directly to a hard number that you can test in a lab. And guess what? It works. Perfectly.
So let's just hammer this point home because it's the most important part. The photon isn't secretly vertical or horizontal and we just don't know which one. No, it is genuinely, physically in a superposition of both states. That strange combined state is its reality, right up until the moment it interacts with that crystal.
So you can see how this leads to some pretty profound consequences. I mean, if things really exist in this haze of possibilities, what does that say about reality itself? It turns out it means that the very act of looking at something fundamentally changes it.
In Dirac's own words, there's just no such thing as a passive observer in the quantum world. To see a photon, you have to interact with it, and that interaction inevitably disturbs it. You can't just quietly peek at the quantum world without affecting what you see. This is why things get so weird. You can't observe the before without totally changing the after. Here's the punchline. The superposition represents all the possible realities for that photon. The act of measurement,
the interaction with the crystal, it forces that whole cloud of possibilities to collapse into one single definite outcome. So the observer doesn't just discover reality. In a very real way, they kind of help create it.
Now, you might be thinking this all just sounds like some far-out philosophy, but physicists needed a way to actually work with these ideas, and that meant they had to invent a completely new mathematical language, one that was designed from the ground up to describe this world of possibilities. And to do this, Dirac came up with this absolutely brilliant notation. The state of a quantum system isn't just a number, it's a mathematical object called a ket vector. Really, you can just think of this symbol as a kind of container, a single package that holds all the information about the system's potential states all at once.
And this is what that language actually looks like. Now, this isn't an equation you're supposed to solve. It's more like a sentence. It literally says, the state of our photon is a certain amount of the parallel state plus a certain amount of the perpendicular state. Those little numbers, C1 and C2, tell you the weight or the influence of each state in that superposition. Square them, and you get the exact probabilities we were talking about. This is how the abstract philosophy of maybe gets turned into precise, powerful mathematics.
And so, we end here with the question that has haunted physicists and philosophers for a century now. If superposition is the fundamental rule, and measurement is what forces a choice, what does it even mean for something to be when no one is looking? The principle of superposition doesn't just describe the world, it forces us to ask what it even means for a world to exist at all.